Have you ever just looked around at everything? The air you're breathing, the water you drink, even your own body. It's all built from these tiny little atoms linking together. But how? How do they know how to connect? What are the architectural rules they're all following? Well, today, we're going to dive into the invisible forces that build our entire world, chemical bonds. So get this. Our story kind of kicks off back in 1985 with a discovery that was, well, just plain bizarre. Scientists found a totally new form of pure carbon they nicknamed the buckyball. And it was a molecule made of exactly 60 carbon atoms, all arranged in a shape that looked literally like a perfect soccer ball. And this thing presented a really fascinating puzzle. I mean, how did 60 separate carbon atoms just know how to link up into such a perfect, stable, and completely symmetrical sphere? What invisible rulebook were they reading from? That's the core mystery we're going to unravel today. To figure out how atoms build stuff, you first have to understand what motivates them. And in the world of chemistry, that motivation is one thing and one thing only: stability. And the main rule of the game that guides this whole quest for stability is called the octet rule. You know, the rule itself is surprisingly simple. Atoms just feel happiest or most stable when they have 8 electrons in their outermost shell. These are what chemists call valence electrons. Think of it like trying to complete a set of H trading cards. And to get that full set, atoms will do just about anything. They'll gain, lose, or even share electrons with other atoms. Okay, so if the goal is to get to 8 outer electrons, how do they actually do it? Well, they've basically got 2 main strategies, 2 main moves they can make. They can either just completely transfer electrons from one atom to another, or they can team up and agree to share them. And this leads us to our 2 main types of chemical bonds. And you can see the 2 playbooks right here. On one side, you've got ionic bonds. These are like a straight-up transaction. One atom gives an electron away, another one grabs it. Simple. This creates charged particles that then stick together. But on the other side, covalent bonds are much more cooperative. It's more like they're roommates deciding to share electrons so that everybody feels like they have that complete set of 8. But, as we all know, sharing isn't always equal, right? Some atoms are way more electron greedy than others. This natural pull an atom has on electrons is called electronegativity. So when 2 identical atoms share, it's a perfect, even tug of war. That's a pure covalent bond. But if one atom pulls harder, the electrons hang out closer to its side. This creates what we call a polar bond, with one slightly negative end and one slightly positive end, kind of like a tiny magnet. So we've got the rules and the strategies atoms use, but how do we actually visualize any of this? Well, chemists came up with this really elegant and simple tool called a Lewis structure. It's basically a 2D blueprint that shows us how all the atoms and their outer electrons are laid out in a molecule. And here's the basic recipe for drawing one. First, you just count up all the available electrons. Then you arrange the skeleton of the molecule, make the first connections with single bonds, and then you just sprinkle the rest of the electrons around to make sure every atom, if possible, gets to satisfy that super important octet rule. It's actually a pretty fun little puzzle to solve. Okay, so these Lewis structures are fantastic 2D maps, but there's a problem. Molecules aren't flat. They live in our 3D world. So how do we make that leap from a flat blueprint to the actual real-life shape a molecule takes up in space? Let's take a molecule we all know and love, water, H2O. Its Lewis structure, its blueprint, is super simple. You've got one oxygen atom sitting in the middle, and it's bonded to 2 hydrogen atoms. But, and this is the crucial part, the oxygen also has 2 pairs of electrons that are just hanging out, not involved in any bonds. We call these lone pairs. Now, if you just look at that flat drawing, your first thought is probably, yeah, sure. It looks like HOH would just be a straight line, right? But the reality is completely different. And the reason why is, well, it's pretty fascinating. The answer has a really long name, VSEPR theory. Yeah, I know, it's a mouthful. But the idea behind it is incredibly simple. Electrons hate each other. Since they're all negatively charged, they repel one another. Think about trying to push the same ends of 2 magnets together. All those electron pairs around an atom, both the ones in bonds and the lone pairs, are going to push each other as far apart as they can possibly get. They want their personal space. So, let's go back to water. Those 2 lone pairs on the oxygen atom are like big, puffy clouds of negative charge. And they are actively pushing on the electrons in the bonds to the hydrogen atoms. shoving them down and away. And what's the result? The water molecule isn't a straight line at all. It has a very distinct, bent shape. And what's amazing is that this one simple principle lets us predict the shapes of all kinds of molecules with incredible accuracy. Just look at this. If an atom only has two groups of electrons around it, they flee to opposite sides, making a straight, linear molecule. If it has three groups, they form a perfect flat triangle shape called trigonal planar. And with four groups, they arrange themselves into a 3D pyramid shape called a tetrahedron. It's all just geometry, driven by electrons trying to get away from each other. So at this point, you might be thinking, okay, bent, linear, tetrahedral, so what, right? Why do we care so much about the specific 3D shape of a molecule? Well, it turns out that shape, it determines pretty much everything. Probably the most important property that a molecule's shape determines is its overall polarity. Remember those polar bonds, the ones that are like an unfair tug of war? Well, whether the entire molecule is polar or not depends completely on how those little tug-of-wars are arranged in 3D space. Let me show you how this plays out. In a symmetrical molecule like carbon dioxide, you have two oxygen atoms pulling electrons, but they're pulling in perfectly opposite directions. Their tug-of-war is a perfect tie. The poles cancel out, making the whole molecule nonpolar. But in an asymmetrical, bent molecule like water, the poles don't cancel. This makes water a polar molecule. And that single fact is why it can dissolve salt, why we have oceans, and why life as we know it is even possible. The shape dictates the function. It's that important. And so, that brings us full circle. We started with the buckyball, this incredibly complex structure that seemed like a mystery. But now we see it's all just governed by a few surprisingly elegant rules. Achieve a stable octet, form bonds to do it, and then arrange yourselves in 3D to minimize repulsion. And it really makes you wonder, doesn't it? If these are the simple rules that built our entire world, what incredible new medicines, materials, and technologies could we design just by mastering them?